Okay, good morning, everyone. Welcome back to class. Let's get started here. So it's the 24th of October. We're finishing our 10th week. Exam 3 will be open next week, opening on Monday. So we're going to pretty quickly finish off Chapter 4 today, maybe have a small amount of time to review. I did go ahead and post a review recording here for you guys too, so you can watch that. And of course, remember our packet of review problems here along with a key. So those are quite good and pretty thorough list of questions that you can use to practice. Okay, so that'll be next week, and it's just chapter 4. Okay, so same kind of conditions as before. It'll be at the testing center. You can bring a piece of paper for notes. Maybe let's talk about that right now. What would be relevant for this next exam? So let's see that the probability is chapter 5. The two quantitative variables is chapter 6. The inference for two categorical variables, this is chapter 5 as well. So this section over here, this is the chapter 4 focused stuff, right? So definitely you want all of this in here. Over here on the left, we will still need to have this. The rest of it, not so much. Okay, and then you'll need to know this right here. Okay, so it's sort of a minimum amount of stuff you'd want to have on that exam for your formula card. Of course, you can put anything else you want on there, so I'll leave it up to you for that. Do you have any questions about the exam? If I remember correctly, I think there's about 12 questions. Just plan on 12 to 15 questions, 2 hours for it, and you can bring any calculator you want. And for some of the problems, there will be some GeoGebra outputs, just like on exam 2. So again, to get the best idea of exam kinds of problems, go through these questions, these practice problems, do the homework. Okay, so all right, so if there's no questions, we'll get back into what we were doing last time. And much of what stats is, after you learn the basics of chapter 3, much of it is pretty much the same stuff. It's confidence intervals and hypothesis testing. What's different is the structure of the data, and that's what's going on here. We're doing hypothesis testing and confidence intervals, but the structure of the data is different. What we're doing here in the last part of chapter 4 is comparing data across two groups. Okay, and so it's very similar, except that the structure is just a little bit different. Okay, so we have two groups. We have people in two different states or two different countries or two different genders, two different political parties, and we're comparing them, differences about them, right? So in this example, which is on page 132, we're looking at the age distribution for actresses and actors. Okay, and so these were in major motion pictures, and we already spent a lot of time talking about this, so you'll hopefully remember this from Tuesday. We're trying to see if leading actors kind of have maybe longer careers, right? If maybe the average age for leading actors is a little bit older than for leading actresses. That's what we're trying to figure out. Okay, so we have our sample over here. So we had a sample of 84 leading actors or actresses. We had another sample of leading actors. For the leading actresses, the average age was 35.6. For the leading actors, the sample mean was higher, 44.7. And then so we set up our hypotheses. And so again, much is similar, but there are some differences. So the similarities are that we still have a null and an alternative. Okay. The two symbols there, the null is still the hypothesis of equality, and the alternative is some difference. So that's the same. We still have parameters, in this case mu, right? So we still have parameters like we did before, but the thing that's different is this other side of the inequality or the equal sign. It's usually up until now, we always had a number over there, right? We were trying to figure out if the proportion of uh, you know right-handed people is equal to some number or greater than some number, right? But here we're looking to see if a parameter is equal to or different to another parameter. And the reason why is because we have two populations we're dealing with. We have the population of leading actresses and we have the population of leading actors. So this is for all of those major motion pictures. So, how long has Hollywood been doing these? Probably at least, 80 plus years, I would imagine. So there's quite a big pool of these leading actors and leading actresses. And so that's what we were drawing from here. And that's the picture. So we have two populations and we get a sample from the first population, we get a sample from the second population. So we talked about how to write out these hypotheses, right? The null, kind of the skeptic's hypothesis, it's sort of the boring hypothesis of no difference, is that they're equal to each other, okay? And that would be fine. It's nothing wrong with that. It's just that it wouldn't require any further research. Whereas if there is a difference for the alternative researcher's hypothesis, then that would sort of, at least you would, probably want to follow up with further research on that, right? So the alternative here is that the leading actresses mean is less than the mean age for leading actors. So this is one way of writing it. It's perfectly fine. If you do that on the exam, 100% perfectly fine. There is a second equivalent way of expressing those two, and that's by subtracting mu actor from both sides. These are both, well, the first one's an equation, the second one's an inequality. So we can, move mu actor to the other side. And so an equivalent way of writing the null is to say mu actors minus mu actors equal to 0. In other words, there's no difference between the two means. And then the equivalent way of expressing the alternative would be to say that mu actors minus mu actor is less than 0, which is the same as saying actresses are, on average younger than leading actors. Okay. All right. So, so we have the hypotheses, but we need to get a p-value, right, to be able to test them. So first of all, just an amazing fact that comes to us from mathematical statistics. It says, okay, if you have a normally distributed variable, okay, so basically like an x bar, right? We know that the sampling distribution of x bar can be normal if certain conditions are met. Okay, so if you have an x bar that's normally distributed, so let's imagine that the actress's x bar is normally distributed. If you have another normally distributed variable, okay, and you subtract those two, then the difference itself is also normally distributed. That normal distribution is just sort of, it's quite powerful and very flexible. So basically, the difference between those two normally distributed variables can also be normally distributed. Okay, so that's the idea. So we're still using a normal distribution for the difference between the two x bars. So that's great. Now, it's the same thing from earlier in chapter 4. We don't know the standard deviations, the population standard deviations, so we have to estimate those with the sample standard deviations, which will put us into the t-distribution. Okay, so all of chapter 4 is t-distribution. Okay, so we're in the t-distribution, but that's okay. We know how to use that. Well, we can be if the conditions are met, right? So what are the conditions? So just like with all of these other inferences that we've done all semester, we're going to have to be checking the requirements before we do this. Okay, so the requirements are here on your formula card. You don't need to memorize them. So make sure you bring this with you to the exam. Now, the first three are going to sound very familiar. Okay, we need to have randomness, we need to have independent observations, and we need to have large enough samples. Okay, so those are actually the same as before, almost the same. Why do we have two? Why do we have to check this twice? Well, because we have two different samples, right? So So it's the same idea, but we have to apply it to both of our samples. Okay, so we need randomness, independence, and then a large enough sample size. There is a fourth one, and that's because we now have two different populations. So it turns out that the two populations have to be independent of each other. Okay, so the population of leading actors has to be distinct from the population of leading actresses for this to work. Okay, so it's just one other thing to check. So there's two different kinds of independence that we have to look for now. Okay, the first independence here is the within sample independence. So with one of those samples, the people in that sample have to be independent of each other. And then the second kind of independence is the people in one sample have to be independent of the people in the other sample. Okay, so it's like intra-sample independence and then inter-sample independence. Okay, all right. So let's go through that. So do the data come from random samples? So let's look back up here. It says yes, this was random sampling. So we can say says random. Okay, and then secondly, the observations are independent. So it's the same rule of thumb. We need to make sure that the sample is less than 5% of the whole population. Okay, and usually we don't know the population size on these sorts of things, right? So we do the next best thing, which is to see how large of a population would we need to make the sample small, right? So I'm going to go N1, which is 84. That's got to be less than 5% of all of the leading, we'll call this actresses, right? So we'll let the first group be the actresses and the second group be the actors. Okay. Well, because both sample sizes are the same, right? They're both 84. Typically we'd have to check it twice for both of the samples, but it's the same size. So we're just going to end up with the same calculation if we do it for the male actors as well. So we just have to do that once here. Okay, so we divide that out. And let's see here. So we're going to go 84 divided by 0.05. So 1680. Okay, so as long as there have been 1,680 leading actresses for major motion picture films, then this sample will be small and the people in there should be independent of each other. That's a bit of a, I have a bit of a question mark around that. I don't know if there's been 1,600 major motion picture films in the last 70, 80 years. Maybe there have been. I guess it's possible, right? If they have like 10 films a year for 100 years, that would be 1,000. So it's possible, right? But we've at least done our due diligence there to solve for n, the capital N there. Okay, so both samples are normal, or the sample size is large enough. If we look at the histogram, we have reason to believe that these are not coming from normally distributed populations. Okay, both of these look right skewed to me. So so you do get some older actors and actresses, but it's sort of not the norm, right? Most of them are kind of bunched up towards kind of younger ages. So I wouldn't say these are coming from normal populations at all, but that doesn't matter. As we've discussed, the central limit theorem will kick in as long as there's at least 30, right? And there is more than 30, right? 84 is more than 30. Okay, and then the samples are independent. Well, yeah, I don't know, those two populations are non-overlapping, right, as far as I know. So the samples are independent. So right, the population here, right, there's no overlap that I'm aware of between those two populations, right? So all right, so we've got the conditions met, which means we can go forward with the analysis. Okay, so what would we do at this point? Well, we need a z-score, so I'm sorry, a t-score, so we can get a p-value, right? So there is a formula for the test statistic. It's right here. Okay, so if you're doing a two-sample t-test for a difference of means, you take the test statistic right? So x bar 1 minus x bar 2, okay? So let's actually calculate that just to kind of think about this a little bit more. So if we go x bar actress minus x bar actor, that's going to be 35.6, right? It's this number here, minus the 44.7. So from our samples, what is that point estimate for the difference? So if we go 35.6 minus 44.7, negative 9.1. Okay, so before we do the formal test, let's just think about what that means. Okay, negative 9.1 is not 0. It is indeed less than 0. Okay, so just looking at that point estimate from the samples, it does seem like there's evidence that on average leading actors are older than leading actresses, right? But who knows? Maybe this is just due to sampling error. We've seen sampling error. Maybe we just because of chance, we got a sample of actresses that were younger. And then if we did this again, maybe the next sample of actresses would be older. And who knows, maybe we got just a bunch of older actors in the actor sample. And if we did this again, we'd get younger actors, which would make the point estimate closer to 0, or it might even switch over, right? It might even become positive, right? So who knows, right? We just don't know until we get a p-value, right? And so that's what we would do, right? We would find this point estimate, and then we'd subtract 0, which is the difference between the null values there, and then we would divide by this expression. At first glance, this is kind of hard to look at, but if you focus on it, you'll see that this is basically the standard error, right? What's s squared over n? That's the standard error that we've seen before, right? It's basically this piece right here. Okay, so a t-score is more or less the same kind of structure as a z-score. You have your observed minus the mean divided by a measure of the spread, right? So there's a lot that's similar and parallel to what we've done before. Now, you can do that by hand if you want. I'm not going to do it here in class, and I'm not going to recommend that you do it in this class. You can, though. There's a formula for it. What do I recommend? Software. Okay, so let's run over to GeoGebra, and I'll show you how to do this pretty quickly in GeoGebra. So we're going to go to the toggle, the 3 dots, probability calculator. We go to the statistics panel and then the drop down. And I think you can tell by now by this part of the semester, we've gone through like 4, maybe even 5 of these various inference procedures. Okay, so that's good. But it does mean it can be a little bit harder, determining what procedure to use. So the first thing we think about is this a test or an estimate? Well, estimates are confidence intervals. We're doing a test, right? So it's one of these. Then we think about the kind of data we have. Okay, so age is a count of the number of years you've been alive, right? So that's quantitative, which means we're working with means. So the proportions are out. So it's one of these. Then we think about, the other, we keep thinking about the structure of the data. So we're looking at a difference between 2 populations. So the single mean is out. So yeah, we've narrowed it down to these. And what have we always said about inference about means? Well, for our class, it's always the t-distribution. And honestly, that's the vast majority of the of all of stats. If you're doing a difference between 2 means, it's very typically going to be a t-test. Okay, so we go t-test, difference of means, and notice that it doesn't even let us change the null hypothesis. I can come in here and try to type in numbers, and it's just set, right? And that's probably not a bad thing, honestly. So notice they're using the second version there. So the null is that there's no difference. right? So it'd be kind of interesting if there were a difference, right? That would be something that you would talk about maybe, right? Because it's interesting. So that's why I think of the null as sort of the boring skeptic's hypothesis, right? There's nothing to see, nothing here to think about or consider. It's just that, it's the same, it's zero, right? So then the alternative is that it's less than zero. So let's see here. So we're going to go less than. So we put in the mean for the females. The sample mean was 35.6 with a standard deviation of 11.3, and there were 84. And then for the leading actors, we'll go 44.7, 8.9, and then 84. One other thing, make sure you do not select the pooled. Okay, the pooled, you would use pooled if you had reason to believe that the standard deviations in the two populations were the same. And we don't have reason to believe that here. And so it's basically just a big assumption. And, sometimes assumptions are good, but typically that it's just not going to be the case that it'll be pooled. Okay, so for our class, always leave this unchecked. Okay, so we're not going to pool the standard deviations together there, and we've got it. Okay, we have a t-score of negative 5.8. Okay, so it is possible that we would get a difference of negative 9.1 years, even if there is actually no difference between the two populations, but it would come with a t-score of negative 5.8. It would be almost 6 standard errors away from the null value. And we know that once you get past 2 standard errors or so, it's in the unlikely territory. So by the time you get up to 6 standard errors, we know it's almost impossible for that to happen, right? So we turn that around. We basically say, well, it's almost impossible that the null is true, right? And so the p-value confirms that it's 0. And then I believe that's 7 zeros in there. It's just so many zeros. It's hard to count it, right? So it's very, very unlikely that these two population means, are equal. Okay, so we'd reject the null. Does that make sense? So let's write those down and come to our conclusion here. So the test statistic is the t-score because we're in the t-distribution. So it's negative 5.7983. So we're going to take that p-value and do what we've always done with it. We're going to compare it to alpha. So 0, 1, 2, 3, 4, 5, 6, 7, 1, 7, 8. If you're looking at your GeoGebra and it says 0, it's because of rounding. So if you want to change your rounding, you'll hit the gear, and then, for example, if I put this on 3 decimal places, then it'll just say 0, right? Because rounded to the third decimal place, it's a 0, right? So that's why I always like to leave mine at like kind of this extreme value here of 15. It's an eyesore, but at least I don't have to worry about rounding issues. Okay, so what is alpha? Well, it kind of depends on what industry you work in. Are you working in business analytics? Are you working for a pharmaceutical company? So anyway, for this one, it's 0.05. Okay, so the p-value here is definitely less than alpha. So since the p-value is less than alpha, we reject the null. The null was that there's no difference between the two population averages. Okay, so we're pretty sure that there is a difference, and that the mean age for leading actresses is less than the mean age for leading actors. Okay, so we would say there is sufficient evidence to conclude that the alternative is true, but we don't say alternative is true at this point. We're trying to put this into plain language, so we would say that the mean age of leading actresses, and so this is all, we're not talking about the people in the sample, we're talking about all leading actresses, is less than the mean age of leading actors. Okay. So, it's an interesting problem to think about. So like labor economists study this sort of thing, like differences between different sectors, or maybe between like genders when it comes to pay and other things here. So it's kind of an interesting problem, I think. What next? What would we do after we establish that there's a difference? Okay, so this establishes that there's a difference. I mean, we can always be, there's always the chance we make a type 1 error. Okay, so we're not saying with 100% certainty, but we're saying we're basically sure that there's a difference here. What would we do after that? Well, the next logical step would be to estimate the difference. Okay, the hypothesis test doesn't say if it's a large difference. When we say it's statistically significant, we're not saying that it's a big difference. We're just saying that there is a difference. Okay, so that difference could be 20 years, or it could be a half a year. Okay, but the hypothesis test doesn't give us any idea of how big the difference is. It just says that there's a difference. And so the next thing that we would want to do is try to estimate that difference, right? If we know there's a difference, then the next step would be to go to a confidence interval and actually estimate the difference. So that's what we'll do now. We'll see that we can also do a confidence interval for the difference between two means. Okay, so that's the next step. So or typically that's kind of how we operate. We'll do a hypothesis test to see if there's a difference. And then if we are convinced that there's a difference, then we will go forward with a confidence interval. Okay. So let's do that. So we're going to pick up another inference procedure here. And I think you can kind of get the feel for how stats works now. Once you understand hypothesis testing, confidence intervals, then you can very quickly start picking up more confidence intervals and hypothesis testing, right? It just sort of everything slides into the slot, and it's very easy to just pick up more and more different types of data structure. Yes, Armand is saying, can you repeat how you conclude that the fourth criteria is met? So there are two kinds of independence. Okay, so the first kind of independence is considering each sample by itself, right? So you have the sample of leading actors, and we have to make sure that within that sample they're independent of each other. Okay. The second kind of, and then you have to do the same for the females, right? For the actresses. Then the second kind of independence is between the two samples. So we have to make sure that basically the two populations are separate, or more or less separate, and we don't want to get people from one sample in the other sample at the same time, right? And as far as I know, there's never been anybody who's won best leading actor and like leading actress, right? So I'm pretty sure those two are independent, right? Does that make sense? Okay, so you basically look at the two populations, and if they're more or less non-overlapping, then they're independent of each other. Okay, so good. All right. So that's what we'll do now. If we're pretty darn sure that there's a difference. Of course, we don't want to be like arrogant about it. Of course, there's always a chance of being wrong, but it's past the standard for concluding that there's a difference. So once we've done that, we'll try to estimate that difference with a confidence interval. Okay, and so what parameter is the interval estimating? Well, it's actually a parameter of parameters. Okay, so the parameter that the confidence interval is estimating is actually the difference between two parameters. So that's kind of interesting. So it's getting a little bit meta here, right? So we've got parameters, and then the new parameter is actually a difference of two other parameters, right? But it all still works. So the way I think about it is this. We're trying to estimate this mu actress. I'm just going to go F for female and M for male just to save some space here. There is some true difference. Well, there is some value there between, when we subtract those two, we get some number, right? It could be zero, but we think it's not, right? It could be positive, it could be negative. We're pretty sure it's negative. But it does exist somewhere, right? So it's somewhere on the number line. Let me do kind of like extreme values here. It certainly has to be, between 100 and negative 100, right? So, it's somewhere on the number line. We just don't know what it is, right? So we think it's probably negative, okay? And so what we do is we estimate it with X bar actress minus X bar male, right? And so we already did that, right? We found that was negative 9.1. Okay, so that's our point estimate. And then what we'll do is we'll put a margin of error on both sides of that point estimate. So hopefully that sounds familiar to you. So we have our point estimate in the middle, and then we add a margin of error on the right, and then the same margin of error on the left. Okay? And so what are we trying to accomplish here? We're trying to capture that parameter, right? We're trying to estimate how big that difference is between the two, right? So negative 9.1 is our point estimate. It's one point on the number line that estimates the true difference between those two parameters, okay? And so because of sampling error, we know it's probably not exactly negative 9.1. That's our best number, but we're at the same time, we know it's a little bit off, right? So, but we just don't know if it's more than that or less than that, okay? And so that's what the confidence interval will do for us. It'll give us a range of plausible values for that difference in the two parameters, okay? So how does it work? Well, we have to check the conditions, okay? The good news is we've already done it, right? It's the same four conditions, so we don't need to run through that again. So we've already checked conditions, and we're basically ready to go. So let's go over to GeoGebra, and we already have all the information in, so this goes really quickly once you do the hypothesis test. It's an estimate, okay? And so it's not a test this time. It's going to be an estimate, right? That's what confidence intervals do, is they estimate. And it's not a proportion. This is quantitative data, so we're in the means. And then we know there's two populations we're looking at, so it's not this single mean, it's a difference of means, okay? And then, so we know it's a t estimate difference of means. And since we already just did the hypothesis test, all of the information's in here, okay? So very easy and ready to go. Okay, so the answer's down there. Let me run back to the formula card real quick just to show you what GeoGebra is doing. I don't expect you to do this by hand. You can if you want, but it's not really the focus of our class. So the midpoint, the point estimate is that negative 9.1, and then we're going to go plus or minus the margin of error. Okay, so we have a margin of error. That's the formula for the margin of error. What is it? Well, it's just like all of the other margins of error formulas that we've seen, right? So remember from earlier in the chapter, right? So notice that it's the same structure. We have a critical t-score, and then we have this expression here that basically averages out the two standard deviations. So it's a measure of the standard deviation. Okay, so it's a critical t-score times the standard error, and that gets us the margin of error. So it's a very similar idea. The equation looks a little bit different because it's a different data structure, but it's a very similar kind of parallel idea to what we were doing before. Okay, and that's good. So here we go. It uses the formula. It gives us our point estimate in the middle, negative 9.1, plus or minus, and then we see the margin of error right here. Okay, so it's negative 9.1 plus or minus the 3.1. Okay, so let's write that down. So we have negative 9.1 plus or minus 3.1. Okay, so if I add that to negative 9.1, so if I go 9.1 negative, and I add 3.1 to that, I get my right endpoint of negative 6. And then if I go 9.1 1, negative minus 3.1, I get negative 12.2. Okay. All right. So what does that mean? Let me clean this up just a little bit here. It's in agreement with our hypothesis test, right? We're pretty sure that the average age for females is less than the average age for males, but it could be anywhere between negative 6 years of a difference all the way up to negative 12.2 years. Okay, so on average, leading actresses could be as little as 6 years younger than the leading actors, or as much as 12 years younger. Okay, so we like that. It gives us an idea of the error term, right? And oh, sorry, I'm trying to find GeoGebra here. Okay, so yeah, that's what it's telling us here, right? The lower limit is negative 12.2, and then the upper limit is negative 6. Okay, so the hypothesis test and the confidence interval kind of go hand in hand there to help us understand what it is we're studying. Any questions there about that? Okay, so anything dealing with the t-distribution, I'll have to give you some kind of GeoGebra output, right? So, so for you have a problem or two on this, and you'll have like a screenshot from GeoGebra that you'll interpret. So again, to give you a clear idea on that, go to those practice problems in the review session that I recorded. All right, let's go back to the notes here. And so let's write down the confidence interval. So the confidence interval is negative 12.2 to negative 6. Okay, and so how do we interpret it? Well, the first interpretation is just like the other interpretations we've done before. It has the same exact 3 parts to it. So we would say there is, or we are, 95% confidence that the difference between the mean age of leading actors and the mean age of, let's see, I don't want to go out of order here. So the of leading actresses and the mean age of leading actors is captured by the interval from negative 12.2 years to negative 6 years. Okay, so if you say that, perfect, 100%, that's fine. But because the data is a little bit more complicated, the structure of the data is a little bit more complicated, there's a little bit more that we can think about and say here. So that's a perfectly fine response, but there's a couple of other aspects I want you to think about. I want you to think about the values of this interval and whether or not 0 is included in the interval. Okay, so what is the significance of 0 in the interval? Well, is 0 in this interval? Okay, so if we look over here at our interval that we've drawn, this might be 0 right there, yes? Okay, notice that 0 is not in the interval. 0 is not in the interval. Okay, so 0 is not in the interval. The interval is a list of plausible values for the difference, right? So it's saying that 0 is not a plausible value here. Okay, so do you see how that's in agreement with our hypothesis test? So the 2 sample confidence interval actually, in a way, sort of contains within it a hypothesis test, like a 2-sided hypothesis test. If 0 is not in the interval, then it's equivalent to basically rejecting the null hypothesis of no difference. Okay, so the the confidence interval actually kind of already does a hypothesis test for us. So it's kind of interesting that way. So I just want you to be aware of this other fact here. We can say since 0 is not in the interval, and all of the values in the interval are negative, we conclude that there is a difference and that the leading actresses are on average younger than the leading actors. Does that make sense? So you don't need to say that second part, but I want you to be aware of it. You might hint get a multiple choice question about where 0 is in the interval. So just be aware of this, and be prepared to understand what it means to have 0 in the interval or not. Okay. So I'll just tell you outright. You'll see something like that on the midterm or on the final. Okay. So when you do these 2 sample confidence intervals, just think about 0. Is 0 in the interval? Is it not in the interval? It'll show up on an exam soon enough. All right, so I want you to try this, and I'd just like to note we picked up 2 inference procedures in under an hour, right? In just about 40 minutes or so, we picked up 2 new inference procedures, and that's because we've already seen hypothesis testing in confidence intervals several times now, right? So it kind of like picks up speed here. Because we kind of have the framework all put together and we understand it, and so we can just sort of keep seeing these new types of data and just fitting it into the same slots, right? So it's really quite nice at this point in the semester. Okay, so if there's no questions, I want you guys to try one of these. If you look on the next page, there is a data set about education. Okay, so education is another big, industry sector of the economy, society, etc. So we're always thinking about education as well. And there are, analysts, scientists, statisticians who are studying education data all the time. And what this study does, this is called the National Assessment of Educational Progress, sometimes called the NAEP exam. Okay, and it's one of these big standardized exams that we use to just kind of get an idea of how education is going in the country. So I believe there's everybody, at least in the public schools, is supposed to get this exam once or twice, or maybe even more during their time in the schools. So in 2004, there was so we have some data here from a couple different samples. So we have a 2004 sample, we have a 2008 sample. So in the 2004, there were 1,013-year-old students, and then in the 2008 sample, there were another 1,013-year-old students, right? So I guess junior high kids, right? And so for the 2004 sample, the mean was 257. But again, not everybody gets the same score, right? Some are going to get higher, some are going to get lower. So there's spread in the population, and we measure that with standard deviation. And in 2008, the mean was 260 with the standard deviation of 38. Okay, so the question is there sufficient evidence that the mean test score was higher in 2008? Okay, so it kind of, the sample mean was higher. It went from 257 up to 260, but is that really significant, right? Or is it statistically significant? Okay, so first, before we think about practical significance, we always think about statistical significance, right? So, so what does the picture look like here? Well, we've got all of the 13-year-olds, all the kids who were 13 in 2004, right? So So this is the 2004 cohort. And then we have the group of 13-year-old students who were 13 in 2008. Okay. And so there's millions. I would imagine there's at least a million 13-year-olds, right? At any point in the country, maybe a lot more than that. So when you have a million people, unless you work for the company that administers the test or the department that administers the test, you can't really get your hands on all the data, right? So we have a sample, and so we have 1,000 students from the 2004. And so what label should we use on the subscripts? I'm thinking we'll just use a single digit there. So we'll have the X bar from '04, we'll have the X bar from '08, right? And so in 2004, it was 257. In 2008, it was 260. Okay. So it looks like maybe there's something there, but who knows? Maybe it's just 3 points. Maybe that's not statistically significant. But we still need to, we don't know until we have a p-value, right? Okay. So what I want you to do is I want you to write down the hypotheses. Okay. Then I want you to check the requirements. And once you've checked those requirements, then you can run over and use GeoGebra to get yourself a t-score and a p-value. And then you can actually make a decision whether or not this is statistically significant. Okay, let's give this a try. I'll go quiet for about 5 minutes and let you, let's go for 6 minutes here. So at 12:22 here, we'll come back together and see how you do with this, right? Okay, good. So give it a try, guys. This is page 134 of the lecture notes. Okay, so question for you. What would be more interesting, that there is a difference or that there's not a difference? What would be more interesting? What would require further research? If there is a difference or if there's not? In other words, what would that alternative be here? The researcher's hypothesis. Let's see here. Good, that there is a difference, right? So that's the alternative. So how do we talk about difference here? Well, there was a mean in 2004. Okay. But we don't know what it is. Okay, because maybe we don't work for the agency that does this exam, right? Maybe we're just an independent researcher, or we're at a different institution, and so we don't really know what that average is, right? Um, so there's two of them. There's mu 4 and there's mu 08, right? And then the data, right? So we have data on all of these kids, and so each one is a score. It's the count of the number of points they receive on the exam. So it's quantitative. So we're looking at mu. So the null kind of skeptics hypothesis is that it's equal, and then the alternative is that we think maybe that the test score is higher in 2008. Now, if we have no idea, you know, if we're kind of the first people to study this sort of thing, we would probably do a two-tailed test. But it might be something that people have thought about before. Usually, it is with education, and so somebody for anecdotally or for whatever reason they might believe that it was just higher in 2008. So we might have a good reason to think that it's a one-tailed test here, right? And that's what they're saying is was higher in 2008. Okay, now alternatively, we could write this in the form mu04 minus mu08 equaling 0, and that would be equivalent to mu4 minus mu8 being less than 0. Okay, so those are equivalent to each other. The second form is a little bit nicer for going over to confidence intervals. Okay, then we check the requirements. Okay, so these are the 4 requirements from your formula card. So first of all, the data come from 2 samples that are random. Okay, well, yeah, we have 2 simple random samples here. So it says random. Okay, the observations are independent. So notice that both samples are the same size. So typically you'd have to check it twice, but because the sample sizes are the same, it's going to give you the same exact calculation both times. So we don't have to, do it twice here. So we'll just divide both sides here by 0.05, 0.05. So that should give us 20,000. And yeah, sure enough, there's more than 20,000 13-year-olds. I don't know how many there are, but definitely more than 20,000. Okay, so then both samples are normal. Okay, well, we don't know that they're normal, but that doesn't matter because we have large enough samples, right? So we would just say, well, 1,000 is definitely greater than or equal to 30. So the central limit theorem will kick in. Fourth, the samples are independent of each other. Well, yeah, if you were 13 in 2004, if you were in that cohort, you weren't 13 in 2008, right? So the people in the two populations are distinct and not overlapping, right? They're independent of each other. Okay. So let's look at the sample data. Okay, so the best way of testing this is to look at x bar 4 minus x bar 8, right? So that's what we're going to look at here. So we go x bar 4 minus x bar 8. So let's see. In 2004, it was, in 2004, it was 257. And then in 2008, it was 260. So that's a 3-point difference. -3 is not 0. It is indeed less than 0. Okay. So, so we do have evidence in favor of the alternative, but how strong is that evidence? Okay, 3 points to my eyes doesn't seem like a big deal, but remember, we're not thinking about practical significance yet. We first consider statistical significance. And so that's more about p-values and alpha and test statistics, right? So we're all ready to go. If you want to do this by hand, you can. Okay, we set up the t statistic here. I recommend using GeoGebra. Okay, so let's reset all this. So we go toggle, 3 dots, probability calculator. We go over to statistics. Then this is a test, right? And we know it's a difference of means. Okay, the null is already set up for us. In fact, we can't even change it. The alternative is the less than, right? We leave the pooled undone, unchecked, and then we put in the sample statistics. So we had 257, we had 39, and we had 1,000. Then we had 260, we had 38, and we had 1,000. Okay. So we have our test statistic. So we're about 1.7 standard errors away from the null value, okay, for a p-value of 0.04. So it all depends. I mean, so that's relatively low, but it depends on what your alpha value is. So so let's write those numbers down and come over here and look at the alpha value. So the test statistic is the t-score. We are in the t-distribution here. It's negative 1.742. And then alpha, the p-value is 0.0408. Alpha is 0.1. And sure enough, the p-value is less than alpha. Okay, so since the p-value is less than alpha, we reject the null. Okay, so this, we're throwing that out. We're rejecting that in favor of the alternative. So in this case, when we reject the null, we are saying there is sufficient evidence to conclude that the alternative is true. Or in other words, to conclude that the mean in 2008 is higher than the mean in 2004. We don't say how much larger it is. Okay, it could be 100 points higher, it could be 1 point higher. We're just saying it's statistically significant difference, right? We're not saying it's like a big difference. We're not saying it's a practical difference. We're saying it's a statistically significant difference, okay? So, is that a practically significant difference? Who knows, right? That would be the job for, an education researcher. Maybe a 3-point difference would mean a huge difference, right? Maybe it wouldn't, right? So, but we do know that there is a difference, or at least we're pretty sure of it, okay? So once we've established that there's a difference, what would we want to do after that? Well, we'd like to estimate the difference. Okay, this doesn't estimate the difference, it just establishes that there's a difference. So the next step would be to use a confidence interval to do that. But before we do that, let me just see if you guys have any questions here about what we've done. Anything you want to ask me here? Great. Well, let's do the confidence interval then. The great thing here is that once you've done the hypothesis test, the confidence interval, when you're using technology, is very easy. It's just you click a button, right? Just like a single button, and you've got it. All right. So we want to so we're sure there's a difference, or we're as sure as we can be anyway, that there's a difference between the two. So we want to, oh, I forgot to mention one thing. When you're doing this homework, you'll sometimes find that you get a test statistic that has a different sign. You might get a negative instead of a positive test statistic, or vice versa. And it'll come down to which one you choose to be your first sample. Okay, so sample 1, I chose the 2004 group. Sample 2, I chose the 2008 group. But there's not really anything, like fundamental about that. I could have chosen sample 1 to be my 2008 and sample 2 to be my 2004. I don't want to confuse anybody, but I just want to show you what would happen had we done it in the reverse order. Okay, so if I had reversed that, which some of you will do in the homework because it's not really, it's, you know, there's not like a fundamental difference there. Notice that I get this, I have to switch my order, right, on the inequality, but notice I get the same p-value. The t-score is the opposite, right? And that's just because I've changed the order there for the samples. Okay, um, so it's very common to do that because again, nobody's, you're not forced for, the females or the 2004 group to be the first group. We could have had males first and then the 2008 group. So just keep that in mind. You should get the same equivalent result at the end, either rejecting or failing to reject, but your test statistic can be a little bit different. Okay, so just keep that in mind. All right, so suppose we want to estimate the difference between the average score on the national on this NEEP test for 2004 and 2008. Okay, so if I do mu 2004 minus mu 2008, there will be some number for that parameter of difference, that difference of parameters, right? So we're estimating a parameter of parameters here. Okay. So how does it work? Well, it's going to be somewhere on the number line, right? And it's probably going to be somewhere between like, like negative 100 and positive 100, right? Those test scores typically aren't going to be revolutionized over, 4 years or so, right? So typically the difference would be pretty close to zero. We're pretty sure it's negative here because it's actually improved, right? So so maybe it's here, mu4 minus mu8. So what do? Well, we take a difference, right? X bar 4 minus X bar 8. And we did that up here. We found that to be a negative 3. Okay, so there's our point estimate, negative 3. And what we do is we put a margin of error on the right and a margin of error on the left, right? So we're going to go margin of error on the left and then margin of error on the right. I said that backwards, but anyway. So there's our confidence interval. And with some luck, we'll capture the difference between those two parameters, right? So let's do it. Okay, so let me go back to what I had before. 57, 39, 260, 38, right? So this is the order we had in before, right? Like this. So if we switch over to the confidence interval now, there's not any work to do really. You just have to come down here and click on this and then it works. Okay, so we have we want 90% confidence here. And we've got it. Okay, we've got our point estimate of negative 3 and our margin of error negative plus or minus 2.8. Okay, so I'll go negative 3 plus or minus 2.8. So we'll have negative 3 plus or minus 2.8. Okay, so let's pull out the calculator here. So if I have negative 3 plus 2.8, that gives me a negative 0.2. And then if I go negative 3 minus 2.8, that's negative 5.8. Okay. So what does that mean? Well, it means that the difference between those two means could be as little as 0.2 points, so like a fraction of a point, or it could be as much as about 6 points. Okay, so we'll have our kind of traditional interpretation of the confidence interval first. Okay, so we'll say we are, or there is 90% confident that the difference between the mean 2004 score and the mean 2008 score is captured by the interval from negative 5.8 to negative 0.2. So you say that, it's perfect. Everything's great. But because this is a little bit more complicated with the structure of the data, we want to think about 0, okay? 0 is not in that interval. So since this is an interval of plausible values, it's not plausible that this number here is 0. That's just not plausible, okay? So what does that mean? Well, it means that there's a difference, right? So the other thing we would say is since 0 is not in the interval, and the interval consists entirely of negative values, we conclude that the score 2008, the mean, is higher than in 2004. Okay, so just be aware of that idea of 0 being in the interval or being not in the interval. You know, kind of a hint, you'll see something like that, some kind of question, conceptual question about that on either midterm 3 or the final, almost for sure. Okay. All right, so it took a little bit more time than I thought it was going to, but I think that's okay. I mean, we did a nice thorough discussion there of the rest of chapter 4. Are there any questions there that you want to go over? Let's see, I've got a question in the chat here. So on the test, we don't have to do that. I don't have to do that, right? Hold on. On the test, we don't have to write that though. Oh, yeah, that's right. Yeah, I'm not going to require that you write that out. But what it'll look like is there'll be a multiple choice question about confidence intervals, and it'll involve 0. But for the written part, this should be perfectly fine. Does that answer your question, Gillian? Yep. Okay, good. All right. Any other questions? Okay, so 11 minutes is not really much to review that we can do. So that's why I always make these recorded reviews for you guys. So it's here in the announcements, this video from a couple semesters back. It's pretty recent, definitely very relevant. So you can watch that. Definitely do all the problems in here. So maybe for 10 minutes, let's crack open this document here and consider this for a little bit. So what is chapter 4? In a nutshell, it's the statistics of quantitative data. So it's the basics of working with quantitative data. Chapter 3 is categorical data. Chapter 4 is quantitative. So it really is the beginning of how we study quantitative data. So when we begin that study, we talk about the tables that we use. So the main table is the frequency distribution. Okay, so that's where you take a quantitative data set and you put it into bins, right? And then you count the number in each bin. Okay, once you have that, then you can consider statistics and graphics, right? So the graph would be, it could be a box plot, it could be a histogram. So let's think about the various graphics that you may see on the midterm. Okay, so for quantitative data, there's the dot plot, there's the stem and leaf plot, there's the histogram, there's the box plot. Anything else I'm leaving off? We talked about the normal probability plot. Okay, sometimes called a quantile plot. There's just different various names for it. So those are the plots you should be aware of. Let's see here. I don't want to spend a ton of time on plots because I think it's a little bit easier than some of the other stuff. Okay, yeah. What I'd like you to be able to do is to take a raw data set and find all of the key numbers by hand, except for the standard deviation. You don't need to do this one by hand. Okay, but the rest of these, if I ask you for the median or the mode or the range or something, I'd like you to be able to do that by hand. So the number of goals scored by a random sample of 16 hockey players. So if we have that raw data set, how can we find all of these numbers along with the 5-number summary? I'm going to just add in there 5-number summary. How would we do that? So we put the data in order. So 0, 2, 3, 5. Oh, I missed a 4 in there. Oops, there's a 4 and 2 5s. Okay, then let's see, a 6, 3 7s. What comes next? 10. 19. 21, 24, 30. Yes? So 16. Good. All right, so let's do the 5-number summary first. The 5-number summary is min, Q1, Q2, Q3, max, right? So to get those, we need the overall median. So if we have 16, 16 is even. So we're going to go 8 in, 1, 2, 3, 4, 5, 6, 7, 8. And then we'll go 8 in from the right, 1, 2, 3, 4, 5, 6, 7, 8, right? So we take the average of the middle two. So the average of 7 and 7 is 7, right? So for the 5-number summary, 1, 2, 3, 4, 5 things here. So the min is 0, the max is 30, the median is 7. Then we need Q1, Q3. Okay, so Q1 is the 25th percentile. It's basically the median of the lower half. So we split off the lower half. There are 7 in the lower half. And so 7 is an odd number, which means the median is right there in the middle. So 4 is the first quartile. Then the third quartile is the median of the upper half. Okay, and since there's 7 in there, there's also 1 right there in the middle, which is 19. Okay, so we have the 5-number summary. The mode is the number that occurs the most frequently, which looks like 7 to me. The range is going to be 30 minus 0, or 30. And then the mean, we're getting low on time. I don't think you need to watch me add up all these numbers and divide by 16. It would just be the sum of those numbers and divide by 16. Okay, good. So just some kind of basics of just checking to make sure you know how to take a raw data set and get some summary of the data set. The other thing you'll probably see is a box plot. Okay, so very common for us to put this on this third midterm because the box plot is sort of it's so versatile. It kind of tells if any one graphic can tell the whole story, it's going to be the box plot. So be prepared to know how to create the box plot. Okay, so again, I don't want to spend all of my time on graphing, so I'm going to keep moving on here. With histograms, we can and box plots, we can talk about the shape here. So it says choose the histogram that best matches the description given. The distribution of number of times individuals in this age group log into a social networking website during the day tends to be right skewed. So that would be this one right here. Right? This is right skewed. This one's left skewed. And this one is more or less symmetric and bell-shaped, right? So no skew there. So the right skewed one is the one on the left there. Okay, let's say we have a box plot and the median is to the left of the center of the box and the right whisker is longer than the left line. Okay, so let's just draw that out. If the median is to the left of the center of the box, well, that means Q1, Q2, the median, and Q3 are looking like this. And then it says the right line is longer than the left line. Well, this means that half of the data is spread out here, and then the other half is spread out over that distance. So it's tighter, it's denser around the left side. So if it's denser, that means the peak will be taller. And then over here, it's less dense, so the peak will be shorter over there. So what am I getting at? This would be a right skewed data set. Okay, so that's kind of the basics of describing data. After we do that, we'd like to start with the inference. We'd like to do confidence intervals and hypothesis testing. So for us to be able to do that, we need a distribution, a sampling distribution. Okay, so we need to know how, basically how X bar behaves. Okay, so so how do we do that? Well, we know that for X bar, if certain conditions are met, it will behave like a normal distribution. Okay, so let's look at, we're getting a little low on time here. So the amount of soda a dispensing machine pours into into a 12-ounce can of soda follows a normal distribution with mean 12, standard deviation 0.06. So let's, maybe in the spirit of like quality control, we'll think about taking a sample. So if we take a sample of 36 cans, then basically we're going to have an X bar from the sampling distribution of samples of size 36. So what would the mean for that sampling distribution be? Well, if the parent population is 12 ounces, then we would expect our X bar to also be about 12 ounces, right? But because of sampling error, it's going to bounce around a little bit. So that bounce is called the standard deviation or the standard error. How do we measure that? Well, that's sigma divided by the square root of n. So sigma is 0.06, and then n is 36. So it's going to be 0.06 divided by 6, which is 0.01. Okay. All right. So what's the shape? Well, because the parent population is already normal, then the sampling distribution will also be normal. Okay. All right. So let's stop there, and then let's plan on leaving Tuesday open for the exam. Okay. So we won't meet here. I will be available. So if you want to meet with me during that time, I can meet with you on Zoom. So just let me know, and then we'll plan on meeting back as a class here on this Thursday. So a week from today, we'll meet back and get, so towards the end of week 11, we'll meet again and get going with chapter 5. Okay. So are there any questions as we break here for the week before you guys take your exam? Okay. So there's still lots of time to study. So yeah. And so let me know if you have any questions. Email me today, tomorrow. If you email me on the weekend, sometimes I can answer those, but I'll definitely get back to you on Monday if you don't hear from me on the weekend. So have a good one, guys, and good luck with that exam. I'll see you all back on Tuesday. Okay, thanks, Julia.